Okay, so second test in the set is the 2017 test. That's the second one. And so we begin at the beginning. This video is going to be part A. Okay, first question, vectors and scalars. So what's a unit for a vector? So let's go over the vectors. Mad 5. Momentum, acceleration, displacement, forces including weight, impulse, velocity, and all the fields, electric, magnetic, and gravitational. So keeping that in mind, let's take a look at these units. Watts measure power. Power is not in the list, so it's not a watt. Kilogram measures mass. Mass is not a vector, so it's not kilograms. Seconds measure time. Time is not a vector, so it's not 4. But newtons measure force, and that is a vector, so that's choice 2. Alrighty then. Next question. Number 2, displacement vector with magnitude of 20 meters could have perpendicular components of what? So if I have my components are perpendicular to each other, the way that would look is that if I have x component and y component, and then there's the resultant, that makes a right triangle. Make this one B. So you have like two components at right angles, a squared plus b squared equals c squared. So when which pair is going to give me in that relationship of where a and b, like for instance 10 and 10, this would be a and this would be b. And it's like this 10 squared plus 10 squared equal 20 squared. No way. 10 and 10 in the same direction make 20. At right angles, they definitely do not. It's also not choice 2, because 12 and 8 in the same direction make 20. They're not going to make 20 at right angles to each other. So we're left with 12 and 16. In the same direction, they make 28. And opposing, they make 4. So that's worth noting about vectors. So it's either choice 3 or choice 4. Choice 3 has a range of 4 meters to 28 meters, and choice 4 has a range of 8 meters to 24 meters. So choice 3, 12 and 16 opposing make 4, in the same direction make 28. 16 and 8 in the opposing make 8, in the same direction make 24. So I'm going to have to check a squared plus b squared equals c squared on each of those to see which one makes 20. And so checking number 3, doing a squared plus b squared equals c squared, where a is 12 and b is 16, c does wind up being 20. It's also a 3, 4, 5 right triangle because 4 times 3 is 12, 4 times 4 is 16, and what's 4 times 5 but 20? So yeah, it is a form of a 3, 4, 5 right triangle. And then if I do a squared for number 4, I'll squeeze it in here. 4, a squared plus b squared equals c squared. For that guy, 16 meters squared plus 8 meters squared equals c squared. C in that case winds up equaling, that's 18 meters, so it's not 20 meters. So it's not choice 4, it's choice 3. All right, next question. Okay, number 3, we have 1 kilometer south, 3 kilometers west, 3 kilometers north. What is the distance traveled by the hiker, not the displacement? So distance is a scalar, and we simply add it up. So I don't care about south, I don't care about west, I don't care about north. I just say 1 plus 3 plus 3. That is 7 kilometers. Choice 4. If we actually wanted to find the displacement, you have 1 kilometer south, 3 kilometers west, 3 kilometers north. I misread that. So this would be the actual displacement. 1 kilometer south, 3 kilometers west, 3 kilometers north. I can kind of cut off that 1 kilometer and just make a right triangle with one side is 2 and one side is 3, and do a squared.
Please film a shortcut for the morning news.
Plus b squared equals c squared. And so the displacement is 3.6 kilometers, but that's not what they asked for, so it is not choice 2. They want the distance. Just add them up, 7 kilometers, choice 4. All right, number 4. So we have initial velocity 60 meters per second east, slowing to 6 meters per second east in 4 seconds. What's the acceleration during the 4-second interval? So there's two different ways that you can do this. You can use the definition of acceleration, delta v over t, or you can use the first kinematics equation, Vf is Vi plus At. It doesn't matter, but remember that delta is final minus initial, so A is Vf over V minus Vi over t, so V final is 6 meters per second, V initial is 16 meters per second, and the time that it takes is 4 seconds, and so 6 minus 16 is negative 10, and negative 10 over 4 is negative 2.5 meters per second squared. And if the initial velocities were east, that negative means that it's 2.5 meters per second squared west. And so that is going to be choice 1. And so that is choice 1. And then number 5, we have surface of planet X, a body with a mass of 10 kilograms, weighs 40 newtons. What's the acceleration due to gravity on planet X? Let's look at the weight equation. And so weight equation is acceleration due to gravity is weight over mass. Weight is 40 newtons, mass is 10 kilograms. 40 divided by 10 is 4 meters per second squared. And so that is going to be choice 4. It's not 9.8, by the way, because we're planet X, not Earth. Not Earth. So it's not choice 3. All right. Also, it's not the weight. Choice 2 would be if you did 40 times, no, we have the weight. It's 40 newtons. So I don't know how you get 400 or 4,000. But yeah, it's 4 meters per second squared. Number 6. We have V initial, 8 meters per second. We have V final, 14 meters per second, 44 meters. What is the acceleration of the car? So I know Vi and Vf and D, and I want A. Only one way to do this. So don't forget to square Vi and Vf. We get 196 equals 64 plus 88A. So now solve for A. Subtract 64 from both sides. I need to do this math anyway, so I might as well just kind of do it. 196 minus 64 is 132. And we have 132 is 88A, so divide both sides by 88, and I get an answer. And that answer is... And I got 1.5 meters per second squared, and that is choice 2. All right, that's the first column on June 2017. Let's go after the second column. So number 7. Object starts from rest and falls freely, free fall, for 40 meters near the surface of planet P. The time is 4 seconds. What's the acceleration due to gravity on planet P? I'm putting the displacement down as negative. It's falling downwards 40 meters, so that is a downward displacement. So D is negative 40 meters. Time is 4 seconds, and since it's free fall, falls freely, I know my acceleration is due to gravity, negative 9.81 meters per second squared. Whoa. My bad. See that? You do problems too quickly, and you make mistakes. It is not 9.81 meters per second squared. We are on planet P. Planet P. Man, they're loving different planets on this region. So I don't know what G is, and in fact, it wants me to solve for what G is. But I still have enough information to solve for G, which of course is the acceleration. And so with the information that I have, I can do D is VIT plus 1/2 AT squared, and VIT goes away because my VI is 0, and so I have negative 40 meters is equal to 1/2 times A times T squared, 4 seconds squared. And when you run the math, you get negative 5 meters per second squared. It wants the magnitude, which is just an amount, and so 7 is choice 3. Next question. Ooh, look at that. Here's a vocab term, in equilibrium. What happens when you are in equilibrium? Well, so at baseline, if you're in equilibrium, you have no net force. The forces cancel. So then there's no acceleration, and your velocity is constant. So if the block is in equilibrium, the acceleration is straight up 0. Be careful when you say constant but not zero. That's true of the velocity. Velocity is constant, but it could also be zero. So the velocity could be zero and still be in equilibrium. But it's talking about the acceleration, and there's no acceleration if you have no net force. Next question. So we're on number 9. We got angle of reflection. I know that the incidence angle equals the angle of reflection. And so my angle of reflection is, of course, 30 degrees. Just kidding. It is not 30 degrees. We do not measure from the surface. We measure from the normal, right? So we have the incident ray, 60 degrees. Let's see if I can sketch out. Bang, 60 degrees is my refracted ray. Let me grab a protractor and see if my sketch is pretty good. Boom, how you like me now? That's 58 degrees. I nailed it just by eye. I am that good. Anyway, yeah, I'm so proud of myself. So angle of reflection equals incident angle. It is 60 degrees, choice 2, not 30. We don't measure from the boundary. Okay. And also, for what it's worth, the reflected ray is as I drew it. It is not this guy. This is not the reflected ray. No, this is not even a thing. We reflect off of the boundary over the normal. And the last problem in this column gives us a force. It talks about an electron and Lenz's electric field strength. Formula for electric field strength. All right, E is F over Q. So I stick in the force and then I stick in the Q. But wait, it didn't tell me the Q. Or did it? I have an electron. So I know that the Q of an electron is -1 elementary charge. But when I'm doing E equals F over Q, I actually need to use the Coulomb charge, the 1.6 times 10 to the -19 coulombs for my electron. So -1.6 times 10 to the -19, and I get a field strength in newtons per coulomb of 9.4 times 10 to the 4 newtons per coulomb, and my force was 2 sig figs, so my answer is 2 sig figs. Alrighty, that's the first page. Now let's go to the second page with number 11. Looks like we have some kind of collision momentum situation. Let's take a look. 7 kilogram cart A, 3 kilogram cart B are initially held together at rest on a horizontal frictionless surface. Compressed spring attached to one of the carts is released and the carts are pushed apart. This to me sounds like an explosion problem in momentum. As after the spring is released, the speed of cart B is 6 meters per second, and what's the speed of cart A? Okay. So P before equals P after and P equals MV are the two equations we're going to use. The rest of the stuff is not on the reference table, but let me walk you through how to get there. I don't like telling you guys just to memorize stuff out of context just because I said so, right? Everything in physics, of all the stuff, nothing is because I said so. Anyway, so the total momentum before, we have the two carts. Total momentum before P1 plus P2 before equals P1 plus P2 after. We use prime for after. But then before, we're not moving. So that means we have no momentum. So we have 0 before the explosion. And so we have P1 prime plus P2 prime after the explosion. So that means that after, we have the momentum of the first guy equals negative the momentum of the second guy. And we know that P equals mv, so this is the explosion equation. M1 V1 prime equals negative M2 V2 prime. All right, now we put our numbers in. We have 7 and 3. We'll say A is the 7 guy, so we have 7 kilograms times V1 prime, which is what we're trying to figure out, is negative 3 kilograms. Now that negative's not on the mass can't be negative, but it's actually on the velocity. So we have the 6 meters per second for that guy there. So we have 7, V1 prime is negative 18. So I'm trying to solve for V1 prime. I divide both sides by 7, and I get a V1 prime for the first cart of negative 2.6 meters per second. So if B goes off at 6 meters per second, A goes backwards at 2.6 meters per second, but it wants the speed, so I don't care about the negative. Speed is a scalar, and so I have 2.6 meters per second, choice 4. Next question. We have an electron. It's moving in a circle in a magnetic field at constant speed in a circular path. So even though it's talking about electrons and magnetic fields, I think this is a circle question. What's the net force acting on the electron? We need is at position A. When in a circle, the net force on the object is equal to the centripetal force, and the centripetal force we know always points inwards. FC inwards, and so at that point it's going inwards. Inwards would be choice 3 in that context. Alrighty, next question, 13. Okay, 13, so we have 2 volts of potential difference, and we know the Coulomb charge, and we want to know what is the energy. So the formula that we're interested in, V equals W over Q, and we know the voltage is 2 volts, and we know the charge is 8 times 10 to the negative 19 coulombs. That's 5 elementary charges. And we want to know what is the energy, and of course when we're working with electricity, the energy is work. We use W as work for energy when we're talking about electricity. So 2 times 8 times 10 to the negative 19 is 16 times 10 to the negative 19, which is otherwise known as 1.6 times 10 to the negative 18 joules. 1.6 times 10 to the negative 18 joules. My bad if I'm interchanging the times 10 to the negative or E. I consider them interchangeable, so there you go. And so 13 is choice 2. Then we go to the next column with number 14. Gravitational force and electrostatic force between 2 charged particles. Gravity always attracts. So gravity can be attractive or repulsive. I don't think so. Both forces can be attractive or repulsive. I don't think so. And then gravity must be attractive. True. Electrostatic can be attractive or repulsive. Also true. Remember that opposite charge signs attract. Opposites attract. Charge signs attract, and like charge signs, like positive, negative, they repel each other. But gravitational force must be attractive. So that's choice 2. All right. Then we have number 15. We have 2 charges, 3.2 times 10 to the negative 19 Coulomb point charges separated by 0.03 meters. If the distance between the 2 is decreased, then what happens to the force between them? So it doesn't say decreased by how much, just the fact that they're decreased. So the formula, the equation that we're looking at here is Coulomb's law, K Q1 Q2 over R squared, and the distance between them is R. And then so R squared and electrostatic force are inversely proportional. What that means is if I double the separation between the charges, it's going to be 1/4 the force. If I half the separation between the charges, it's going to be 2 squared, 4 times the force. If I third the separation between the charges, it's going to be 3 squared, 9 times the force. But you don't really need to know the inverse square piece of this. It's just saying that as they get closer together, as the 2 charges get closer together, what happens to the force? And so the force is going to increase. So it's not going to decrease. If you're getting closer together, the distance is decreasing. So we're talking about closer together here. So as they get closer together, that electrostatic force is going to increase. So there goes choice 1 and choice 3. But are they attracting or are they repelling? Well, let's look at 14, where I said opposite charge signs attract, like charges repel. These are both positive. 2.2 positive, 3.2 times 10 to the negative 19 coulombs. So they're both positive. They are like charges, so they're going to repel each other. So the force of repulsion is going to increase. All right, 16. We have mercury, electron in a mercury atom. So that right there, that's going to be page 3 of the reference tables. And we're looking at the mercury chart. And we're going from level F to level B. And so we have E photon is EI minus EF. And so in this case, we have EF is our initial, F as in the level, not E final, minus EB. And then we can look those up on page 3 of the reference tables. They are going to be negative numbers. And so F is negative 2.68 EVs, B is negative 5.74 EVs. When you do the math, you wind up with 3.06 EVs, and that's a positive answer because that is an emitted photon because the electron is falling down from an upper level to a lower level. And so that is choice 3. Then, as I'm going along, I'm checking the answers. Yes, 16 is 3. 17. 4 complete waves in 10 seconds. What is the frequency? This is one of the formulas that I said in my review sheet is not on the reference table. Frequency is the number of wave cycles over the time that the waves happen. So we have 4 waves in 10 seconds. And so that frequency is going to be 0.4 cycles per second, otherwise known as hertz. So that is choice 1. And then the last guy in this column, copper is a metal commonly used for wiring houses. Which metal conducts electricity better than copper at 20 degrees Celsius? In order to do that, I'm going to be looking at the resistivity chart on page 4. And it says which is a better conductor. So a better conductor means a lower resistivity, because we have R, resistance is resistivity times the length of the conductor over its cross-sectional area. And so if I want a better conductor, I want a lower resistance, which means that I want a lower resistivity. So let's write down the resistivities of these different materials. We have aluminum, 2.82 times 10 to the negative 8 ohm meters. That sounds pretty good. We have gold, which is 2.44 times 10 to the negative 8 ohm meters. That's even better than aluminum. We have nichrome, which is 150 times 10 to the negative 8 ohm meters. That's crazy high. That's not a good conductor. That's a good insulator. But then we have silver at 1.59 times 10 to the negative 8 ohm meters. So that's the best of the bunch. It's the lowest resistivity, and it is lower than copper because copper is 1.72 times 10 to the negative 8 ohm meters. So not only is silver better than the other 3 choices, it is also better than copper. And a better conductor, meaning a lower resistivity, so therefore a lower resistance. And resistance is against current flow, so a lower resistance is what makes a better conductor. And so 18 is 4. All right, then that's that page. Let's keep going because we have to go to 35 to finish the part A's. And so here's the next column, number 19. Number 19, 20 joules of work on a block, accelerating block vertically upwards. So we are lifting this block, neglecting friction. If the gravitational potential energy increases by 15 joules, its kinetic energy is what? All right, so the work done, the input work is 20 joules, and work equals energy. So you would think that if you did 20 joules of work lifting something vertically upwards, then you would get 20 joules of gravitational potential energy. But we don't. We only get 15 joules. So 20 joules are in, and we only get 15 joules of gravitational potential energy out. But energy is conserved. So the kinetic energy has to be the difference. Because the energy before total energy before, let's say, hey, the total energy in equals the total energy out. And so if I put 20 joules in and I get 15 joules out, I'm going to need another 5 joules of kinetic energy. So the block gains 15 joules of gravitational potential energy, and it also gains 5 joules of kinetic energy. Choice 2. Number 20, one light bulb blows out, the whole string blows out. They must be connected how? Well, they're not connected in parallel. And the reason why I know that is because in parallel, they are independent connections. So if they're independent of each other, if one blows out, the other ones are unaffected. So they are definitely wired in series. And a series circuit, the bulbs, bulb, 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 they have the whole deal with series is that they have only one path to flow through. So they're connected in series, and series is one current pathway. That's the definition of a series connection. So that's choice 3. All right, number 21. We have the wattage of a toaster, we have the voltage, and what's the energy used in 30 seconds. So I know the power is 1200 watts. I know the voltage is 120 volts. I want to know the energy, which when we're solving for electrical energy, we use work for that. And we have the time is 30 seconds. And even though I know the voltage, I don't actually need the voltage because I can do that energy is power times time. So that's 1200 watts times 30 seconds, and that's going to get me 36,000 joules, and that's going to be choice 4. All right, then I thought I was going to wind up doing like a W equals VIT or something, but I don't have I, and I do have power, so I can just do power times time, and I'm all set. I could also do power is work over time, and solve for the work. That works just as well. 22, the rate at which work is done. I love when they say this. And they're trying to trip you up. They do not want to know what the work is, the rate of work. So they want to know what is the power. They're asking you about the power. And you are lifting a 35 kilogram object. So the mass is 35 kilograms, and it says at a constant speed of 5 meters per second. So I know that the speed is 5 meters per second, and it wants to know the power. Well, I know that power is FV, and I know the speed, and I'm looking for the power. Now, they didn't give me the force, they gave me the mass. But when lifting, I'm going to go over here. When lifting, the force is the weight of what you are lifting when at a constant speed. So that's mg. And so that's going to be 35 kilograms times 9.81 meters per second squared. And so my force is going to be roughly 350 newtons. 35 times 9.81, 343. I'll just round it at that point. I think it's close enough. So the power is the weight of that object, 343 newtons, times that speed of 5 meters per second, and that gets me 1715 watts, which when we round to 2 sig figs, because the numbers they gave us were 2 sig figs, that is 1700 watts, and that is choice 1. Okay. 23, the last in this column. Wave transfer travels through medium. It transfers energy only. Any wave, any type, all the time, energy only. That's just a wave fact. Okay. Next column. Glass may shatter when exposed to the sound of a particular frequency. With that particular frequency, glass may shatter. Would that happen to be the natural frequency? That's what it sounds like. This would be resonance. Doppler effect is the only way frequency can change. That's because of relative motion between the source and the observer, so it's not Doppler. Refraction is the changing in direction of a light ray as you go from one medium into another, so it's not refraction. Diffraction is the wrapping of a wave around a barrier while still in the same medium. So it's a direction change of a wave, but you're in the same medium, you're just wrapping around a barrier, so it's not diffraction either. But it's resonance. Resonance is when you hit something you hit it with a wave at its natural frequency. Could be light, could be sound. You hit that object at its natural frequency, it will vibrate along with the wave, but the amplitude of the vibration is going to increase a lot. And so if that's glass and it starts to vibrate a lot, it's going to shatter that glass. So that's what resonance is. But there you go. 24. Which waves need a material medium for transmission? And so light, radio, and microwaves, all of these guys are not the answer, because radio waves and microwaves are forms of light waves, and light does not need a medium. Doesn't need a medium. Technically, that's light acting as a particle, not as a wave. All waves need a medium. When light doesn't need a medium, it's acting as if it were a particle. But sound waves absolutely do need a medium to travel in. There's no sound in space because there's no stuff in space. It's just a vacuum. And so, yeah, 25 is 3. And just to avoid confusion, it is not a circled light, but is not choice 1 or 2 or 4. Choice 3. And again, radio waves are not the sound that comes out of a radio, it's the type of light wave that sends information to the radio. Cell phone signals, Wi-Fi, all work on radio waves. All right. 26. Which type of oscillation would most likely produce an electromagnetic wave? Electromagnetic wave is a fancy way of saying light. And in order to make light, you have to accelerate a charged particle in order to make light. So a vibrating tuning fork is not a vibrating charged particle. So no, a washing machine agitator at work. You have to know what an agitator is, and that's the thing that moves the wash in a washing machine. No. A swinging pendulum. No. All of these things, none of these things are an accelerated charged particle, right? Vibrate a electron traveling back and forth in a wire. Yes, as it oscillates back and forth. I feel like that question is a little bit unfair because in order to oscillate, you have to realize that there's an acceleration that's directly proportional to the displacement. That's simple harmonic motion, and that's not actually in the curriculum. But yeah, I mean, it's like you do need a charged particle. You should know that to make light, and choices 1, 2, and 3 are not charged particles. So yeah, 26, choice 4. 27. So you have monochromatic light passing. Monochromatic means one color, by the way. Passing from water to air at an angle of incidence of 35 degrees. What will stay the same? And that's going to be frequency. So the way they phrased that, you made it seem like it was going to be like a Snell's law or refraction question, but it's not. And it says what stays the same, and that's the frequency. The speed stays the same within one medium, but if you go from water into air, you are switching mediums. And so if you're going to a new medium, the speed will change. And you do have an incident angle going from one medium to another with two different indices. You will get refraction. The direction does not stay the same. And the wavelength, because the speed will change, the wavelength will also change with it because of V equals F lambda. The frequency does not change. The only way frequency can change is through the Doppler effect. Otherwise, when you go from one medium into another, I don't care what the two mediums are, the frequency of that light will not change. Okay, 28. Index of refraction of y is twice as great as the index of refraction of x. As the light ray goes from x into y, what happens to its speed? Well, we can look at this way. N2 over N1 equals V1 over V2. That's from page 5 of the reference table. But you could also look at it very basically as N equals C over V. And so we're going up in index from twice as great as goes from x into y, and the index of y is twice as great. So I have twice as much index, and n and v are inversely proportional. N and v are inversely proportional. So if I double the index, I'm going to have half as much speed because they're inversely proportional. So the speed of the light ray in medium y with twice as much index is going to be half as fast. Choice 1. And again, you can reason it out with the relative index and speed equation. I honestly think that knowing that n and v are inversely proportional is an easier way to look at that. All right, there goes that page. Next page, and we're almost done with section A. So here's the next column, numbers 29 through 31, and here is 29. So for 29, we have ourselves a transverse wave. So if it's a transverse wave, the particles move up, down, relative to the wave motion, up, down. And so I'm not moving to the left and I'm not moving to the right. And this wave is moving to the right. So for point P, this crest is the next thing that's going to be coming along. So P is on its way up towards the crest. So moving towards the top of the page. Next question, 30. You have a conductor is placed in the vicinity of a positive charge. The conductor is attracted to the charge. The charge of the conductor must be what? And then that conductor is attracted towards the positive charge. So if it's attracted, I know that that conductor cannot be positive. It would be repelled. So must be positive? Heck no. Could be positive? Definitely not. Must be negative? Maybe, but it could also be neutral. And so remember that neutral is attracted to charged. And the reason why that's true is because of induction. Let's take a closer look at what's happening here. Distribution of positive charges, and if that's a positive field on the left, it's going to attract negatives, electrons towards it. So if I have 8 positives, I would need 8, 1, 2, 3, 4, 5, 6, 7, 8 negatives. But those electrons are going to be attracted to the positive on the right, leaving this side, the near side, locally negative, and polarizing the far side to be locally positive, but distance matters, and so there's a net attractive force towards the positive object. But the net takeaway of that is that neutral objects can be attracted to charged objects. So it can be neutral or negative, choice 4. 31, baryon is 3 quarks, so we immediately can get rid of 3 and 4. And so let's take a look at what we have here. So plus 2/3, and negative 1/3, that gets us plus 3 over 3, which is plus 1, so that's legal. Plus 1/3, negative 1/3, and plus 2/3. These guys cancel, and that gets me net plus 2/3 E. That is not legal. It's not a whole number of electrons. So that is choice 1. Whole number of elementary charges, I should say. We have 32. So right away it says rubber resting on dry asphalt. That would be static coefficient because you're at rest of 0.85. No units for mu. We know the 60 newtons, so we know the weight is 60 newtons, and we also know that the weight is equal to the normal force, right? Weight equals normal force. Then it says the minimum force needed to start the rubber block moving across the dry asphalt. To start it moving, you need to make a pushing force that is equal to the friction force, this force of static friction. So I want to know the force of static friction, FF is mu, Fn, and I know mu, 0.85, and I know the weight, so I know the normal force, 60 newtons. And so my friction force winds up being 51 newtons, which is choice 3. 3 more problems left in part A. Oh, this one's easy. 33, inertia. Inertia is mass. So which one has the greatest mass? D at 8 kilograms. Don't confuse inertia with momentum. Don't be doing MV to solve for the most momentum. Inertia is not momentum. You don't need to move to have inertia. All right, 34 and 35. 34, static electricity. A rod comes by the electroscope and the leaves split. The rod is taken away and the leaves go back to the way they were. And so what's going to happen is that when, here, let's draw some pictures here. So the positives, we have positive charges, evenly distributed, the same positive charges, evenly distributed in all cases. Positives, 1, 2, 3, 4, 5 in the head. And let's make some in the stem. And we'll put some in the leaves. I'll put one each on each leaf. And so that leaves us with 1, 2, 3, 4, 5, 6, 7, 8 positive charges. And if I draw 8 positives, I'm going to need to draw 8 negatives as well. Evenly distributed to start. So neutral. But then if the positive rod comes by, that positive rod is going to attract the electrons towards it. 1, 2, 3, 4, 5, 6, 7, 8. So those electrons are going to move up from the leaves into the knob. Then the leaves are going to be net positive. They'll repel each other. But once I take that rod away and remove it, the electrons have no outside field pushing or pulling them around, and they go back to the way they were, evenly distributed on that electroscope. So what happens is that the motion of the leaves results in the electrons moving from the leaves to the knob, so that does happen. So not knob to leaves, but leaves to knob, but then back to the leaves as they evenly distribute again. So it's choice 3, not just choice 1. And then finally 35, the last of the A's. We have, says we want to measure current in a resistor. So the best way to do that is with an ammeter. We don't want a voltmeter. You could do it with a voltmeter if you also had something called an ohm meter, but if you want current, use an ammeter. And then ammeters are always in series with whatever they are measuring. So I want that ammeter to be holding hands in series with my resistor. I don't want it to be hugging in parallel with that resistor. In fact, that's going to create a short circuit and set the whole thing on fire, and you'd be very sad. So it is not 3, it is definitely choice 1. And that is the end of this video. The Part A questions for June 2017.